Okay, now that we understand convection, let's see how that is responsible for the pollution from volcanoes staying in the air. Now what we've got in this graph here is a graph of the pressure, density, temperature and speed of sound as a function of height in the Earth's atmosphere. The one we care about is temperature. And what we can see is, to begin with, up to an altitude of about 11 or 12 kilometers, the temperature drops on average as you go up, as we've been talking about, the environmental lapse rate. So this is the normal behavior in the lowest level of the atmosphere, which is called the troposphere. But then when you get to somewhere 10, 12, 13 kilometers, it's actually higher over the equator than near the poles. You hit a layer called the tropopause, and beyond that things go differently. Beyond the tropopause, the temperature actually rises as you go further up. And that gives us a second zone of the atmosphere called the stratosphere. The stratosphere is basically defined as a zone where, as you go up, it gets hotter on average, whereas the lowest level, the troposphere, is where, as you go up, it gets colder. The stratosphere is much bigger than the troposphere, but has a very low density, so there's actually not much mass up there. Most of the weight of the atmosphere is in the lower levels, but you do get this rather strange difference. Now, what's causing this? Well, we said that one of the reasons why in the lower atmosphere it's hot near the bottom and gets colder as you go up is because most of the radiation from the sun is not absorbed by the atmosphere, it's absorbed down at the surface. Whereas in fact you can still radiate from the atmosphere further up, so the regions up here are losing heat but not gaining it, which is one reason why it's so hot at the bottom and not further up. But in the stratosphere things are a bit different. It's because there's some ozone up here, part of the ozone layer, and ozone absorbs ultraviolet light from the sun, and in the process generates heat. There isn't very much ozone up there, but the atmosphere is really very thin up here, and that small amount of ozone is quite enough to heat it up. So in fact it actually gets rather hotter when you're up higher. So it's due to ozone. But it doesn't matter what it's due to, what matters is its effects. Because what it means is that in the atmosphere, when you get convection, it stops when you hit the tropopause and the stratosphere. So let's imagine you have some air heated up at the surface, and let's imagine this air is very wet, so it rises till it hits a saturation point, and then instead of stopping, it rises at a more shallow rate because of the latent heat of the water, the wet adiabatic rate. But it will still stop when it hits the stratosphere, because the stratosphere, the temperature of the atmosphere increases as you go up. So that means it will rather rapidly hit the point where the air is no longer hotter than what surrounds it, so it no longer has a lower density, so it no longer has buoyancy, so it no longer wants to go up. So what this means is that all the weather in the atmosphere, all the convection, all the rain, all the condensation is locked into the bottom level of the atmosphere, the troposphere. It doesn't get above the tropopause. It doesn't get into the stratosphere. The most dramatic manifestation of that is a so-called anvil head cumulonimbus cloud. Here's a lovely example. What you've got here is a big thunderstorm, and it's pushing air up, but the air flattens out at a particular flat top. This is a so-called anvil head. And you often see this for big thunderstorms. And what this is happening is this altitude here is the tropopause, the top of the troposphere. So below here the temperature drops as you go up, above here the temperature rises as you go up. So that means the convection that drove this huge cloud just stops. At this point it can't go any further because it no longer has a density edge, no matter how humid it is. So the clouds flatten out and hit their head against this and don't go any further. So basically all weather happens in the troposphere. Any sulfur dioxide particles or other particles in the troposphere, they're going to get involved in the weather. They're going to be moved around, and sooner or later they will act as water condensation nucleus. The water will get big enough to fall out as rain and get rid of them. But if you can get the dust higher up, beyond the top of these anvil heads into the stratosphere, up there's no condensation, no convection, no water washing these things out. So if a particle can get into the stratosphere, it will stay there a long time.